Good morning, everybody. Just need to do my audio sync test. Meow! I got you. Oh, there you are. You know they've been missing you on the street. Yes, they have. They have been missing. I know you would like to play with your ball. This is your favorite thing in the whole world, isn't it? Yeah. Okay. Go! Alright, audio sync. Give it a 450 today, I think. How is everybody doing today, huh? Pretty good. Excellent. Cool. Oh my goodness. So she does this thing where she has this little purple pom-pom, and she brings it to you and drops it on the couch and waits for you to throw it for her so that she can bring it back so that you can throw it again. It's just like playing fetch with a dog, except that she will only do that on the couch. The sort of locality of the game is the couch specifically, whereas with a dog you can play fetch with a dog anywhere. Anyway, what's your opinion of C++ as opposed to C? Well, I would have to have done C++ a little more in depth than I've done C, but I have a friend who sort of does C++ for a living, and he's like, yeah, it's C, but with all of the, nice things of a modern language, I guess. It was too hot. Oh man, you should have enjoyed that when it was going on, because something tells me it's not gonna last very much longer. You see, I have my cardigan on in anticipation. But anyway, yeah. Oh my god. So, yeah. Anyway, we should probably move into our lecture material. We had been talking about custom types, a mechanism for encoding the class. We were talking about using classes as a way of enforcing data policies. And one of the interesting things about computers is that when you use data, you will often have a mechanism in your mind for how that data should exist and how it should be accessed. This is generally termed a data policy. One of the interesting things about classes is that they allow for the enforcement of data policies in such a way that it's not possible to violate those data policies. This can be extremely helpful for you because it may very well be that you don't even remember your own data policies 3 months into the future when you come back to a project that you had to leave off because you had to make all kinds of slides for a second-year course, and you didn't have any idea how much work it was to actually make all of the lecture slides for a course. But enough about me. So that's one of the very useful purposes of classes, is that they enforce your ability to restrict the manner of access of data. Generally speaking, that's the purpose of having all of these things, all of these fields inside of a class to hold data. Obviously, there's no data policy if there's no data to have a policy over. And that's also the purpose largely of methods. The purpose of methods is to provide a rigorous access framework to the data that you're storing in the class. So hopefully that's, you know. Is anyone planning to shift their winter courses to the summer? If you're in comp sci, that'll be, you know, I'm pretty sure that I'm reasonably certain that one of the very few courses offered by the CAS department that's offered in the summer is this one. And if you're already in this one, then, you know, presumably you'll pass this one. You know, because everybody's going to pass, right? But, yeah. So, one thing that I will give you, I can offer you a little bit of advice about summer courses, having taught summer courses a couple of times myself. Don't underestimate the amount of work that they are. While, you know, you don't quite get to divide the you don't quite get to divide the amount of like the number of credits by 2 to do the summer course, but it's because it's at such an accelerated rate. Citation needed. My experience with summer courses is that, you know, even taking one summer course is, like, because of the accelerated pace, it can be very strenuous. So if you're planning on taking summer courses, if it were me, I would limit myself to one of them, but like 2 if you're really ambitious. You know. But anyway. So that's classes. We did some reasonably extensive demonstrations of that last class. So let's talk about classes and objects. Everything in Python is an object. Everything is an object. So if we load up our Python interpreter, we can tell what class an object is by using the type function. So the integer literal 27 is of class integer. The string literal blah is of class string. And of course, in our previous example, if we, I should probably just load the file from previously, That would be the intelligent thing to do. Code. Classes. Yeah, there we go. So, documents, McMaster teaching, 1MD3, fall, code. All right, Python 3 classes .py. So, okay, I'm just gonna, this is all stuff from previous, so I'm just gonna comment it out. You know what would be really nice? If Python had multi-line comments. But no, of course, there's no need for multi-line comments because we have single-line comments. Why would you need more than one way to comment things? Starting on the Python SAS. Realer. Oh my god. Stop! You'd think I'd be better at computers by now. So anyway, print type of Harry. And you'll see that Harry is of class main.person. So this is an important distinction, right? Stuff that's defined in main is considered a subclass of main, or, you know, the definition is contained within the definition of main, which is a thing that you would expect to be the case. I could comment using the triple quotes. I don't know. There are sometimes they don't like you like that. But what is the final exam format going to be like? Well, it's going to be pretty similar to everything else that's happened so far. It's basically exactly the same as the tests. Is it possible for me to demonstrate the coding part using Python Tutor? Yeah, that would be a super reasonable thing to ask. Absolutely. Okay, I'm just gonna copy all that over. Bing, bang, boom. Oh, it even expands the thing. Wonderful. Yeah. So. Oh my goodness, that's a big thing. So, so this is what a class. I don't think we actually loaded up a class in Python Tutor last time to see what it looked like. So, we've got all kinds of things. We've got functions, we've got children, we've got the init. These are all defined within the class. So there you go. And Harry is a person instance. So there you go. Cool. All right. Neat. So anyway, the class definition defines attributes, properties, variables, members, and methods that are common among all instances of that class. Obviously, it doesn't matter how many different instances you have, they are all defined in the same way. That's the purpose of having a class, right? Attributes of a class or object are referenced using dot notation, a thing that we've already seen how to do. So here's another example. We wish to have a class point. This is point in the Euclidean sense. So let's doop-a-doop. Let's do it in a different Python Tutor window. Why not? No. Python Tutor. No. Python Tutor. Give me. Thank you. Stupid computer. So, we have a class. We are calling it point. We are inheriting from object. Because you always do. We are defining the initializer. Note that the magic methods, or the methods that are defined by default, are always sandwiched in between two underscore characters. That's how Python tells that this is a method that is overwriting one of the default methods that come with the definition of classes. So we're going to take self, we're going to take two coordinates, x and y. So we're going to have a self.x is equal to x, or we should probably name it something else, eh? It might not have a namespace conflict, but oh my god, semicolons. Self.y is equal to y underscore 0. There we go. Cool. And what were our... Yeah. So, we are, in addition to simply defining a coordinate in two-dimensional space, we're going to define some operations which can occur over that point. So, we're going to define a translation function, a translation method. So, call it translate. We'll take self, dx and dy, standing for delta x and delta y. But there's no delta. There's no delta key, so that's we'll use d instead. Apologies to the Greeks. So self.x is equal plus equals dx, and self.y plus equals dy. There we go. Simple enough. Notice that we are including self here. That's a rule. The first argument of any method is self. It is the instance of the class upon which the method is being called. It is the object upon which the method is being called. The first argument. Always, always, always. Even if you don't name it self, that's how Python will treat it. calling it self is actually a convention. It's not a strict rule. You could name this like S, and then you could follow that through like that. However, let me blow that up a little bit for you guys. There you go. That might be a little easier to see. However, it's going to be treated like the instance of the class on which the method is being called, regardless as to what you actually, physically name it. So self is conventional because it is descriptive. It describes what the thing actually is. So let's do another one. Scale. This is reasonably easy. We've got a, let's see, are we taking 2 scale values in the slides, or nope, just 1. Okay, so it takes self and some scale s, self.x. We got times equals? Maybe we got times equals. Self.y. Times equals is, of course, just like plus equals, except it's with multiplication. Let's see if that... Burp. Yep, that works. Cool. All right. Edit. And let's do an interesting one. Is this, yeah. So let's do distance. It will take self, and it will take other. So this is another convention. Because everything in Python is dynamically typed, of course, the same thing applies with the arguments to methods that applies to the arguments of functions. They are not inherently declared with any particular data type. So if you expect it to be a certain data type, then you A, have to use it like the data type that it is, and B, you should probably document it somewhere. So with distance, the idea of this is that we're going to take the Euclidean distance between 2 points. So self is a point. It is the point object upon which the distance method is being called. And other is, in this case, going to be another object of the point class. So it's fairly simple. It's self squared plus other. Wait, no, that doesn't work at all. Self.x squared minus other dot x squared. So that's... No, I'm sorry. Pretty early in the morning, I guess. Although it isn't. Self.y minus other.y. You take the differences and then you square them. And then that whole thing to the power of 0.5, which is the square root. So that is Pythagorean theorem as applied to the difference in 2 points in a Euclidean sense. So there we go. So this illustrates a couple of things that we haven't quite touched on yet. Number one, the use of other to mean another object of the same class. This is, again, conventional, but not strictly enforced. You could call it anything you like. But conventionally speaking, when you are making a method which is an operation over 2 things of the same class, i.e. the class which you are defining the method in, it is conventional to do self and other, as we're going to see when we do equality comparison, for instance. So, overloading equality comparison. So, self.x, so the other thing that is perhaps interesting that we haven't seen so far is that this is a method that has a return value. So yes, methods, just like functions, may have a return value, and all that it takes to return something from a method is precisely what you do when you are writing a function. You just return something from the method. It is correct. The correct way of thinking about a method is to think of it as a function. It is a function with all of the features and all of the it's got all of the advantages, disadvantages, features, and lack of features that you would expect from a regular Python function. The only difference is that it's now existing inside of this environment where it's got data that's that the class carries as being available to it. So that's the only difference, and that you got to use .syntax to access it. So let me see if you've got any questions. Am I looking wider than usual? Oh, that's possible. I am looking a little wider than usual. Well, there you go. Let's see. No, I need the transform. There. Now I'm not quite so wide anymore. Yeah, you ever have, like, stuff show up, you know? Oh my god. Yes, I watch humorous internet videos sometimes. Do we need to write object in the brackets after the class name? Because I do class name, unless there's something I need to pass. No, yeah, it's so... Some things are actually provided by object. In the previous example, when we tried to restrict access to the fields of the class using slots, we actually we had to inherit from object because object contains the definition for slots, and without inheriting from object, you didn't have access to that. So there is some stuff that's actually provided by object, and it's, you know, it's never a bad idea to inherit from object. I don't really understand why some functions in a class need the double underscores on each side. Okay. So, let's see. Okay. So there are some functions that have been provided to every class by default, right? Init is one of them. You can think of this as a system function. When you write your own initializer function, you're actually overwriting a default version of the init function that is provided natively by the fact that you're defining a class. The native version basically doesn't do anything. So, because that is a function that has specific implications, you use the double underscores. It's a way of indicating... It's like you're indicating a degree of integration with Python, with sort of the Python framework that doesn't exist in other classes. So init is automatically called when you define a new instance for that class, right? Like in the Harry Potter example, when we call person, when we define an instance of the class in this manner, we are automatically calling init. However, it's implicitly calling this, right? The fact that Python looks up the init method when you make this invocation and executes it is, to some degree, implicit in Python's semantics. So because it's like a system method, you use the double underscores. And we're going to see more examples of double underscored methods as we go on, but you'll see that they're all like in the category loosely of integrating with things that already exist in Python. But hopefully it'll be more clear to you by the end of all of this. What do we document and why? Whenever you have implicit assumptions, you should document them. So in this particular case, in the case of this guy, if you wanted to get real right down technical with it, you would say something like calculates Euclidean distance between point objects, self, and other. Basically, you should be documenting, you should be providing documentation to tell the user of the function what the function does and what it expects as input and what it produces as output. Yeah, hopefully that's an answer. How would we access this? I mean, what would a user type in, or what parameters would they enter? So in the case of this guy, you would need that's actually the next bit. I was going to show you how to instantiate objects of point class. So we'll just save that one. When do we use other? When you want two objects of the same class. Do they need to mention the class? Yes. Okay, cool. All right. So in order to use this point class that we have defined, you invoke point to initialize it. We are taking two arguments here, the x and y coordinate, so let's just make it 5 and 8. And let's define a second point. Make that 10 and 2. Sure, why not? And then, if we execute that, and, just go to the end, you'll see that we have point instances where x is 5 and y is 8, and x is 10 and y is 2. There you go. That's a very nice visualization. So, if we wish to use, for example, the distance method, we can do it one of two ways. We can print, I'm just going to print it. You can either do point dot distance x and y. What this way of doing it does is it refers to the definition of the class itself in order to extract the definition for the distance method. Or you could print x.distance y. So this goes for the version of, it accesses the same method but by a different path. Instead of looking up the point class in the list of defined classes, what it's doing is it's going with the class that's associated with x. Since we know that x is defined as a point, because it was defined that way up here, we can still access the distance method. So let's visualize. Pull along our timeline here. And our output, in both cases, is precisely the same, as one would expect. So there you go. Doop. Zoom out a little bit? Okay. I can zoom out a little bit. There. That's perhaps a bit better. Yeah. Cool. Anyway. Methods are called using dot notation. The first parameter, named self by convention, is bound to the object. p.move11 equals point.move p11. Yes. So that's sort of what I already demonstrated, but with the distance method. The init method is implicitly called when an object is created. Its parameters have to be supplied at object creation, unless, of course, you make them you provide them with default values. So, just like with a function, if we provide default values, then you don't actually have to provide the argument. It will assume you mean the default if nothing is provided. The same thing is true in classes. Bloop. Cool. By default, this prints out an internal representation, usually the memory address of an object, if you are printing... Okay. Yeah. I got ahead of the code. So, if you define a class, here's an interesting question. What happens if you try to print one? So, let's go back to our Python tutor. So, we're printing distance here. What if we try to just print x? It's a fair question. It says main.pointObject at, and then it gives this. This is actually a memory address. This is a, in C we would call this a pointer, but that is the memory address at which the point object that we're printing is stored, which is an interesting thing. So we can override this behavior by providing a definition for the string method. So in the same way that we can provide a new definition for init, we can also provide a new definition for string. So let's just do that. Definition underscore string underscore self requires no other parameters. Return doop self.x str self.y bing bang boom. So there we go. If we visualize this execution, there we go, you can see that rather than printing off all of that business that looked like what you get when you invoke type, you're now actually getting the printing format that was specified in this line here, which is good. That's much more informative to someone who, you know, understands the point object as being a point in Euclidean space. This is roughly analogous to how you would write it in, you know, by hand, excuse me, mathematics. So there you go. Doop. Doop. So yeah, in this case, they are doing the same thing, but with the person object. A person with the name Harry Potter. So again, the string conversion method is another one of these ones that's provided by default as you're defining a class. However, you know, by providing a new definition for it, we are overriding the existing definition for it. So, yeah, it's pretty useful. Here's another example. By default, equals compares the internal representation, usually memory address, of the object. So, which is kind of interesting, because if two objects are stored at the same memory address, that means that they are the same object, regardless as to what their values are, right? So, there's a fun little thing that you can do with that. So you guys remember aliasing, right? Hopefully. If we comment out this stuff, let's say z is equal to x. Print x is equal to y. Print x is equal to z. Let's execute that. So you can see that the first test that we do is x equal to, oh, well, I guess it wouldn't be, all right. Let me try that again. Let's say that x and y had the same coordinates, right? We visualize the execution. Like, our intuitive mind would say something like, well, they're at the same coordinates, so they're the same point, so they should be equal to each other. However, you can see that Python does not think that they are equal to each other. That's because it's actually testing the memory addresses to see if the objects are being stored in the same location in your system's memory. Now, because z is an alias for x, this the equality comparison between the two of them comes out as true because they are, in fact, being stored at the same memory address. And this is also, I guess, a sort of sly introduction to the fact that all of the rules of aliasing that we learned over lists are also applicable to classes. So, if we wish, what we can do is we can redefine what equality means for objects of the point class in order to make it something a little more intuitive. So, because equality is a binary operation, we need to take self and other into effect, and we would return self.x is equal to other.x, and self.y is equal to other.y. So if we execute this, you will see we now have truth being the case in both of these comparisons. So that's because it's now comparing self.x and other.x, which, of course, are they are not objects of the point class, of course. They are objects of the integer class in the way that we're using them. So because these are of the same, because equality over integers is a very well-defined thing, and it actually means are both of the values here equal, this works. So yeah, another one of these double underscore methods, equality, and it overloads the meaning of your inbuilt equality function, or your inbuilt equality operator. And it turns out that you can actually write methods to this effect with pretty much every operator that you have available to you in Python. You can overload plus, minus, divide, less than or equals to, not equals to. You can redefine pretty much any operator in this manner, which is kind of cool. Questions? Why was thy first example, the family tree one, returning their names instead of this memory pointer? It wasn't. If we go back to the previous example, we were, in fact, we were printing Harry.haircolor, right? So we were actually printing the fields themselves, not the objects. If we were attempting to print the objects themselves, we would have gotten the memory address, just like we did with the point example. What happens if you redefine init int? Oh, int. I believe that redefines integer conversion. So what you're doing here is you're not redefining print for the point class. You're actually redefining string conversion. So if you so the thing about the print function is that it calls the string conversion function implicitly during its execution. That's why we can get away with that's why this is called string. What you're actually overloading is str of point, right? You're overloading the string conversion class. So because there is also the int class, if you were to overload that, I imagine what would happen is you would be overloading the to-integer conversion for the specific class. I think so, anyway. That's all. That all exists inside of the documentation. Python documentation. What is the difference between is and double equals? I'm not sure what is, so yeah. Oh. Oh, okay, that's interesting. I didn't know that. Okay. Does that work? Let me see if that works. So we got L is 1, 2, 3, 4, whatever. H is L. L is H. True. Interesting. I didn't know that operator existed. Thank you, guys. Cool. You could probably overload is as well. Is it possible to redefine the string class or the integer class? Probably. No, what I would do in that case, if you wanted to make modifications to string or integer, if you make modifications to string or integer directly, that might cause problems in, like, many non-specific ways. So what I would recommend is, like, if you wanted, you know, string plus some other functionality, I would define a class, string plus, that inherits from string. And then, you know, you can use all of the stuff that's in string. You can redefine whatever you need to. And that's not, like, messing with the internal representations of strings, which, you know, generally speaking, you probably don't want to do, even though you think you do. Yep. Neat. All right. So, as we just demonstrated, we can override the functionality of the equality comparison operator by providing a definition for the EQ method. So, let's talk about inheritance. Classes can be used to create objects and to define new classes by inheritance. All the definitions of the base class or parent class are inherited as if they were copy and pasted. So, the example here is we have a new class called colored point. So, if we wanted to have red points and green points, etc., we're redefining things a little bit. So the idea of inheritance is that we can take an existing class and provide modifications to it without modifying the original class. As I just said with the perhaps you want to have, like, string plus, you want to add functionality to the string class, it might not be a great idea to override the string class itself. You might break some stuff way down deep in the compiler. You have no idea how something like string or integer is being used, right? Not by yourself or not by other, you know, other programs or other, like, other functions that you are invoking in order to make your program work. You're just probably going to break all kinds of stuff. However, you can provide your own, you can provide a new class for strings, which is based on the original string class. If you go class, let's call it cPoint, if you inherit from point, then you get everything that's defined in here, plus the new stuff that you want to define. So, if you wish, of course, you should always do an initializer. Self, and an X, a Y, and a color. Are they using it in such a way that it would generate namespace? Yeah, okay. So, we'll call it X0, Y0, and C0. And we've actually got a couple of options here. We can do things in the same manner as we did for the other class, but with the addition of the third attribute, self.c. Or another thing that you can do, which is interesting, is you can do point.init self x0 and y0. So this is interesting because it allows you to reuse the code within the class that you are extending. It might, like, this example is relatively facile, right? Like, it doesn't take very much to, like, this is just super duper simple, right? And so it's not very difficult to reproduce. But if you imagined, like, if this were more complicated, the more complicated this gets, the more impetus there might be to use this method as defined rather than, you know, reproduce its functionality within another class. So there you go. And what was the other method that we had? Yes, darken, which is kind of like the make old method that we had with respect to the person class. So darken takes self and no other arguments. Self.c is equal to self.c plus, or no, actually we want to prepend it rather than append it, dark self.c. So if we wished to define x as a C point, and it is blue, and we then call x.darken, and then we print x.color. Please forgive the American spelling, or x.c. You can see that we get dark blue as a result. So there you go. Are nested functions the same as inheritance? Okay, I've got a few questions here. Can we give some practical examples of classes, how they can be used by others in some situation? So there are some more practical examples of classes that we're going to be getting to later on in this set of lecture slides, like calculators and, you know, various things. So I think I'm going to let the slides speak to that to some extent, if that's okay with you. With respect to nested functions being the same as inheritance, like there are similarities, but they're definitely not quite the same thing. They are similar in that you can consider the body of a class to be a namespace in the same way that you consider a function to be a namespace, right? And, you know, you can define many functions within a function in the same way that you can define many functions within a class. The difference is that with respect to a class, the functions exist, like the methods of a class exist, they are accessible through the class, whereas if you define a function within a function, that function, the sub-function that you have defined, is not accessible outside of the function in which it has been defined. So that level of accessibility doesn't exist. So that would be a difference. There's also the issue of data persistence. The namespace of a function only exists so long as that function is executing. It's deallocated when the function terminates. Whereas an instance of a class, the object is defined so long as the namespace that it's defined in exists. So in some way, it's like being able to step in and out of the class namespace whenever you invoke the class. But yeah, it's not the same thing. I can see why you would think that it's similar. In some ways it's similar, but there are some key differences. Although again, the whole namespace thing, I think it would be the most similar part of that thing. Anyway, that's our time for today. If you guys have any more questions, please feel free to ask them in the chat at this point in time. Otherwise, we're gonna see you guys all on the morrow, and we'll discuss classes a bit more. And don't forget to like and subscribe. Like and subscribe. He says as the viewership is already dropping off. Wow, that actually works. That's crazy. Hilarious. Yay! No, that's lie. That's fake news. I do not have another YouTube channel which has millions of subscribers. That is not true. Not even close. Anyway, take her easy, folks. Have a great rest of your week.